Good morning. Welcome, students. This is my third lecture on the continuation of variational calculus. We have been discussing the calculus of variation, out of which we were started with a physical quantity J to find the extremum value of the physical quantity using variational method, and we got an expression for J which is an integral of a function of a functional, because f is a functional which is a function of functions. So as you can see in the second slide, f is a function of y, and yx, which is nothing but dou y by dou x and x. And as we have introduced a parameter alpha, and we have stated the condition for extremum for j, which is dou j by dou alpha will be 0 and at alpha equal to 0. Till here we have discussed in the last lecture. Today we are going to find out the condition in the form of a partial differential equation which is called as Euler equation, on further expanding the integral. Now coming to the third slide, let us find dou j by dou alpha. So we know that j is a functional, that is function of function. So j depends on f. J is a function of f, but f depends on y, but y depends on alpha. Also f depends on yx, whereas yx also depends on alpha. So we have to write dou j by dou alpha in terms of partial derivatives. Therefore the equation 1, which is dou j by dou alpha, is equal to integral x1 to x2 dou f by dou y, because f is a function of y, into dou y by dou alpha, because y is a function of alpha, plus, as we know, f is a functional. Functional means function of many function of other functions. Here we have, in the first term, we have completed the dependence of f on y and dependence of y on alpha. In the second term, we have to write the dependence of f on yx and yx on alpha. So the second term will be dou f by dou yx into dou yx by dou alpha, the whole into dx. This is, we have studied in mathematical classes how to write a differential first derivative using partial derivatives. So once again, dou j by dou alpha is equal to integral x1 to x2. Basically it was a function of f is a function of y, so dou f by dou y into dou y by dou alpha, plus dou f by dou yx into dou yx by dou alpha, that into dx, because we are differentiating, we are integrating in terms of x. So the end point, starting point is x1 and the end point is x2. Now we are going to find out the path of integration, for which we got a minimum value. We will get a minimum value for j. So in other words, we can say we are going to find an extremum path. Now you see the terms in the bracket of the integral. Dou y by dou alpha. Dou y by dou alpha is nothing but eta of x. This was discussed in the last lecture. So yx is nothing but dou y by dou x. So if I want to write dou yx by dou alpha, you just have to differentiate dou eta by dou dx or d eta by dx, because what dou yx is already dou y by dou x. Therefore instead of y, what you put, dou y by dou alpha, you have to put eta. So you just want to differentiate eta with respect to x. That will be nothing but dou yx by dou alpha. So you have to substitute the two terms in the equation 2. So what we are going to substitute, instead of dou y by dou alpha, you are going to put eta, and instead of dou yx by dou alpha, you are putting dou eta, d eta by dx. Therefore equation 2 becomes dou j by dou alpha is equal to integral x1 to x2 dou f by dou y into eta x plus dou f by dou yx into d eta by dx, that into dx. Hope this is clear, this step is clear. Now going to the next slide. We know integration by terms. Integral of two functions is first function into integral of second minus integration of differentiation of first into integral of second. This was studied in the higher secondary school maths classes. Now using that, we are going to find the differential of the second term, which is integral x1 to x2 d eta by dx into dou f by dou x. It was written as dou f by dou yx into d eta by dx. So this will become, we are considering the first function as dou f by dou x. So first function is dou f by dou x into integral of second. Second is, if you integrate second function d eta by dx, it will become eta. So it will become dou f by dou yx into eta. That is the first term. Minus integral of differential of first into integral of second. Differential of first means the first function is dou f by dou x. So differential of first means d by dx of dou f by dou x. Into integral of second means integral of d eta by dx. It is nothing but eta. So the second term of this integration by parts will become integral x1 to x2 eta into d by dx of dou f by dou yx, that into dx. Now as I told you, eta is nothing but a deviation of y. That means the difference in y at a particular x is what I call as eta, or alpha into delta y is called as eta. But we know that x1 and x2 are the end points of the paths. So all the curves or all the paths will end at the two end points. Therefore there will be no deviation in the y value at the end points. Therefore at x1 and x2 eta will be 0, because delta y is 0 at x1 and x2. Therefore eta of x1 and eta of x2 will be 0. Therefore this equation 3, which is nothing but dou j by dou alpha, will become, instead of substituting the terms from the above integration by parts, that will become integral x1 to x2 dou f by dou y minus, since the first term of this integral by parts vanished, the remaining is eta d by dx dou f by dou yx. So the second term, the negative term, will be substituted into the second term of the equation 3. That will become dou f by dou y into eta dx is coming outside the bracket. So dou f by dou y minus d by dx dou f by dou yx into eta dx equal to 0. That is the equation 4, which we started from equation 2. Now, if we multiply equation 4 by delta alpha, as we know that eta into delta alpha is delta y. So, delta, instead of into multiply on both sides, dou j by dou alpha is the RHS of the equation 4. So, multiply it by delta alpha. So, that will become at alpha equal to 0, that will become 0, because you know that delta at alpha equal to 0, delta alpha is 0, therefore the right hand side will become 0. And if you say the left hand side of this equation 5, which is the right hand side of the equation 4, the integral, you can see the integral is not 0. So the right hand side has become 0. So the left hand side has to become 0. Also should be 0. But the integral is not 0 because delta y and dx are not 0. So the term in the bracket should be 0. What is that? Bracket is dou f by dou y minus d by dx dou f by dou yx. So this condition where the bracket of the integral in the equation 5 is 0, that is nothing but a partial differential equation which is called as Euler equation, which can be expressed in many other forms. Therefore, we can say, in other words, if I have a quantity j which is a functional of f, and where f is a function of y and yx, if f satisfies this Euler equation, then the value of j will be extremum. So that is what we conclude. So remember once again the Euler equation, dou f by dou y minus d by dx of dou f by dou yx equal to 0. And if you apply this to a example of a sphere, for you can see in a sphere the extremum paths are shown, the stationary paths are shown. You can have a you know that the minimum shortest path is a circle in a sphere. Even though to reach from A to B we can have infinite number of paths which are more in distance than the circle. If we solve this Euler equation, we will get that it is a circle. I hope this derivation of Euler equation is easy to understand for you. And we will, in the next lectures, we will be discussing about application of Euler equation, and using this equation solving finding the extremum paths for some cases. So with this we end this session. Thank you one and all.